Hello! In this video series, I'm going to introduce you to the checklist tool and demonstrate how to use it. This tool was inspired by the work of Mark Stenzel and research conducted by and with Dr. Gurumurthy Ramachandran. It became a reality thanks to the talented and dedicated Daniel Drolet. Development of this tool was motivated by the fact that the vast majority of our workplace exposure assessments are qualitative, that when the basis for our assessment is professional judgment informed by subjective intuitive inputs, those judgments are wrong almost 2/3 of the time. In fact, they're more likely to underestimate the true exposure. To appreciate how concerning this situation is, let's consider the AIHA exposure assessment strategy and how it facilitates decision making. Under a comprehensive approach, all exposures to all chemicals for all workers must be assessed. So even in a relatively small workplace, this amounts to hundreds, if not thousands, or tens of thousands of assessments. Clearly, it's not feasible to assess all these exposures by collecting personal exposure data. Instead, the strategy directs us to conduct an initial round of qualitative assessments. The outcome of that initial qualitative exposure judgment determines the type of follow-up, such as exposure monitoring, and indeed whether there is any follow-up. For example, if in the initial assessment we conclude the exposure is acceptable, there's no further follow-up except to document our conclusion. This ensures that the limited resources are directed to where they're needed most. Thus, professional judgment plays a significant role in exposure assessment. Since the strategy depends upon qualitative exposure judgments being accurate, our professional judgment must be calibrated. For the purposes of this discussion, I'm referring to the definition of professional judgment listed in the 4th edition of the AIHA Strategy Manual and shown here. Just as a bit of review, under the AIHA strategy, hygienists use a decision chart when used in conjunction with a risk management matrix, like the one shown here. Follow-up recommendations are more likely to be consistent for similar levels of exposure. So as you can see, to drive appropriate follow-up, these exposure judgments must be accurate. Checklists are used in a number of specialized fields for complicated tasks upon which people's lives depend. In fact, experts recommend checklists anytime there are more than 3 moving parts. Prior to the B-17 bomber, flying an airplane was simple, no checklist needed. But the pilots flying this prototype were unable to mentally process all the data inputs associated with its many technological enhancements, and because they forgot about the new control locks, the plane stalled shortly after takeoff and crashed. In exposure assessment, we're also dealing with people's lives, but over a longer period of time. So the attention to detail is still critical. Like the B-17 bomber, exposure assessment has become more specialized and more complicated with a lot more inputs. The checklist helps you focus on the critical details, incorporating them objectively and consistently, producing accurate and consistent exposure judgments. With only a few inputs to consider, it's easy to use, and thanks to our talented partner, Daniel, there's a tool that makes it even easier to use. The tool is comprised of 3 algorithms or heuristics that are based on physical-chemical principles that have been refined empirically through experience. Algorithms were calibrated using exposure scenarios for which sufficient exposure monitoring data was available to determine the reference exposure control category with a high level of confidence. The checklist itself was validated in a series of workshops and the results published in the Journal of Occupational and Environmental Hygiene. The citation is shown here. The gist is that it works well for a broad range of scenarios and is useful for exposure assessors at all experience levels. The tool in its current version is recommended for scenarios involving pure and relatively pure volatile and semi-volatile chemicals, and for fibers, particulates, or aerosols. For the agents you see listed here, a few more steps are required, which will be incorporated into the next version of the tool. There are 3 sections to the checklist, and the first is the rule of 10. It's based on the saturated vapor concentration equation, shown at the top of the slide. The Rule of 10 algorithm accounts for the reduction in the saturated vapor concentration due to different exposure control mechanisms. As you can see, for every incremental increase in the level of control, the saturated vapor concentration is reduced by an order of magnitude. Using this maximum predicted concentration as a surrogate for the 95th percentile, we can compare it directly with the occupational exposure limit, or OEL, to predict the exposure control category in exactly this order. We start by identifying the appropriate OEL. This is important because OELs change over time and differ depending on the organization that set it. Make sure you document the OEL that you use. Next, look up the vapor pressure and calculate the saturated vapor concentration. Oh, and by the way, the checklist tool will do this for you. Working from the observed level of control, and this is the level of control that you observe, for example, mechanical ventilation or local exhaust ventilation, and determine the fraction of the saturated vapor concentration by which the concentration will be reduced from the table shown in the previous slide. Compare this value, the Cmax, to the OEL. This fraction corresponds to one of the exposure control categories. Let's work through an example using acetone as the agent. The first step is to select an occupational exposure limit. In this case, we'll use the OSHA PEL for acetone, which is 1,000 parts per million. Next, look up the vapor pressure, in our case at room temperature for 25 degrees C, so the vapor pressure is 231 millimeters of mercury. Next, we calculate the saturated vapor concentration, which in this case would be a little more than 303,000 parts per million. Then, using the table shown on the right of this slide, we identify the fraction by which the maximum concentration would be reduced for a given level of control. In our case, we're going to say that we have good general ventilation, about 6 air changes per hour. And so, according to the table, we see that the maximum concentration would be about 1/1000th of saturated vapor concentration, or 303 parts per million. Dividing that 303 parts per million by the OSHA PEL gives us a value of 0.3. Comparing this to our criteria for our exposure control categories, we see that it would fall within category 2. The second and third algorithms work off a similar concept, the required level of control, which is the level of control deemed necessary through experience to adequately control the exposure. The required level of control is captured in the vapor hazard ratio table and particulate hazard ratio, respectively. To use these heuristics, we simply compare the observed level of control to the required level of control to predict the exposure control category. For vapors, the required level of control is dictated by the relationship between the vapor pressure and the occupational exposure limit, which we call the vapor hazard ratio. From the table, you can see that there is a vapor hazard ratio scale corresponding to ranges of the vapor hazard ratio values, and that the required level of control increases as the vapor hazard ratio increases. Using the vapor hazard ratio is pretty straightforward, and we start by determining the vapor hazard ratio scale. As you can see in step 4, if the observed level of control is greater than the required level of control, as dictated from our vapor hazard ratio table, then we would conclude that that exposure is likely a category 1 exposure. If the observed level of control is consistent with the required level of control, we would predict a category 2 exposure. And if the observed level of control is less stringent than the required level of control, we would predict the exposure to be a category 4. With the vapor hazard ratio, we used an equation, but the PHR, the particulate hazard ratio, is read directly from the PHR table and corresponds to the range in which the OEL falls. This approach is fashioned after the performance-based exposure control limits, or PBECLs, used in the pharmaceutical industry. In our tool, the PHR applies to particulate fibers and aerosols. This is the same decision logic as for the VHR, minus the extra step. The checklist tool has a database containing about 300 chemicals and their corresponding exposure limits and vapor pressure data. Chemicals not already in the database can be added. Good practice requires that you verify these data against your own scenarios. Otherwise, the only additional information that you need to input is the observed level of control. I encourage you to look for this tool, available at esi@umn.edu/products/. And try it with your exposure scenarios, especially if you have or are going to collect personal exposure data. This will help you calibrate your own professional judgment and increase your judgment accuracy.